6. Equilibria. 6.1 The idea of equilibrium. Chemists usually think of a reaction as starting with the reactants and ending with the products. However, some reactions are reversible. For example, when you heat blue hydrated copper sulfate, it becomes white anhydrous copper sulfate as the water of crystallization is driven off. The white copper sulfate returns to blue if you add water. So you get CuSO4, 5H2O, which is equal to, but it can be reversed back from CuSO4 plus 5H2O. However, something different would happen if you were to do this reaction in a closed container. As soon as the products are formed, they react together and form the reactants again, so that instead of reactants or products, you get a mixture of both. Eventually, you get a mixture in which the proportions of all three components remain constant. This mixture is called an equilibrium mixture. You can understand how an equilibrium mixture is set up by thinking about what happens in a physical process, like evaporation of water. This is easier to picture than a chemical change. First, imagine a puddle of water out in the open. Some of the water molecules at the surface will move fast enough to escape from the liquid and evaporate. Evaporation will continue until all the water is gone. But think about putting some water into a closed container. At first, the water will begin to evaporate as before. The volume of the liquid will get smaller, and the number of vapor molecules in the gas phase will go up. But as more molecules enter the vapor, some gas phase molecules will start to re-enter the liquid. After a time, the rate of evaporation and the rate of condensation will become equal. The level of liquid water will then stay exactly the same, and so will the number of molecules in the vapor and in the liquid. The evaporation and condensation are still going on, but at the same rate. This is called a dynamical equilibrium, and is one of the key ideas of this topic. In fact, you could have started by filling the empty container with the same mass of water vapor as you originally had liquid water. The vapor would begin to condense and, in time, would reach exactly the same equilibrium position. Although the system used here is very simple, you can pick out the 4 conditions that apply to all equilibria. First, equilibrium can only be reached in a closed system, one where the reactants and products can't escape. The system does not have to be sealed. For example, a beaker may be a closed system for a reaction that takes place in a solvent, as long as the reactants, products, and solvent do not evaporate. Equilibrium can be approached from either direction, and the final equilibrium position will be the same, as long as conditions such as temperature and pressure stay the same as well. Equilibrium is a dynamical process. It is reached when the rate of 2 opposing processes, which are going on all the time, are the same. And finally, you know that equilibrium has been reached when the macroscopic properties of the system do not change with time. These are properties like density, concentration, color, and pressure, properties that do not depend on the total quantity of matter. A reversible reaction that can reach equilibrium is denoted by a double-headed arrow. The same principles that you have found for a physical change also apply to chemical equilibria such as A plus B, which are reactants, are equal but can be converted back to C plus D, which in this case are products. Imagine starting with A and B only. At the start of the reaction, the forward rate is fast because A and B are plentiful. There is no reverse reaction because there is no C and D. Then, as the concentrations of C and D build up, the reverse reactions speed up. At the same time, the concentrations of A and B decrease, so the forward reaction slows down. A point is reached where exactly the same number of particles are changing from A plus B to C plus D, as are changing from C plus D to A plus B. Equilibrium has been reached. One important point to remember is that an equilibrium mixture can have any proportions of reactants and products. It is not necessarily half reactants and half products, though it could be. The proportions may be changed depending on the conditions of the reaction, such as temperature, pressure, and concentration. But at any given constant conditions, the proportions of reactants and products do not change.